Okay, thanks everybody for joining us today for the CISL seminar. We're pleased to have Deepak Cherian here, and he's going to present a talk titled Earthmover, Accelerating Frictionless Earth Science Research and Applications. A little background about Deepak. He's a forward engineer at Earthmover, where he works on Array Lake, Ice Chunk, XAR, X-Ray, and other packages in the Pangeo ecosystem. So the Python Pangeo ecosystem, for those that know that. And he's a long-time open source contributor and was previously employed here as an oceanographer in the climate and global dynamics section. So we're very pleased to have you here today and look forward to your talk. Thank you.
Thanks, Doug. It's good. Thanks, Doug. Thank you for inviting me to present. So my name is Deepak Cherian. The title of my talk has changed. I think it is now Accelerating Frictionless Accessibility for the Earth Sciences. That's a lot of words. But I'm hoping to communicate the idea that a group of us are thinking very hard about how to make data more accessible and easier to use. And we think that this is an extremely important problem. My name is Deepak Cherian. I'm a forward engineer today, but I have a long background as a physical oceanographer. Most recently, I was in CGD in the oceanography section, working with ocean simulations and observations. But during my time here, and even before that, it became very clear to me that our software stack was holding the science back. Everything was just too hard and too painful. And I increasingly found myself spending more and more time working on tools that would make my life easy. And then I discovered that made other people's lives easier. And it was just a positive reinforcement cycle. And so I got pretty deeply involved in X-Ray. And since then, kind of expanded to contribute all over the place. And so from there, I now work at Earthmover. We are a public benefit corporation started by Ryan Abernathy and Joe Heyman, who I think most of you know. Joe used to be in CGD too. And so we're a group of scientists, also open source community leaders and participants, and a bunch of seasoned engineers who've built similar data infrastructure at top companies, which is a real revelation to me. I didn't know even the private sector had the same problems that all of us in this room have. Our mission statement is to empower people to use scientific data to solve humanity's greatest challenges. This sounds very grand, but I've been diving into the history of data sharing in ocean atmosphere science, and I think it fits. So the outline for the talk today, I'm going to trace kind of the arc of open data practice in ocean atmosphere science. This is going to be a very kind of personal takeaway, not exhaustive at all. I'll introduce this idea that's come up recently about frictionless reproducibility, and then talk about how I see us at Earthmover putting these two pieces together with what we're building. This is kind of like a very personal talk, kind of that tries to summarize ideas I've had for many years. And so clearly a lot of that's been influenced by many discussions with Ryan and Joe, but also others, including Matt Long and Kevin Paul, who used to be at NCAR and now are at other places, Ethan Davis at Unidata, and Ed Armstrong, who's at NASA at PODAC, the Physical Oceanography Data Center, and Jinbo Wang, who's now at TAMU, but used to be at PODAC too. So I think, yeah, some of their ideas are going to be expressed here. So I'm going to start by tracing the history of data sharing in meteorology. And all of this was very new to me, which was very surprising, and I thought it would be nice to summarize a bit. It's not going to be exhaustive. It's just the bits and pieces that stood out to me personally. I'm really going to quote very liberally from two sources. The first is this WMO report on Resolution 40, which I will introduce. And the second is this report on the Distributed Oceanographic Data System, or DODS. And both of these I thought would be very dry reading. They're not. They are very interesting. I recommend you read it if you have interest in these topics. And so open data practice in meteorology is very old. I think at some level, all of us know this, right? Weather is global, climate is global. We have to talk to each other. There's no other way it could work. But it was really, it was kind of inspiring to read that the history goes back all the way to the 1850s to the first International Maritime Conference in Brussels. And so a group of representatives from I think 10 navies around the world get together into a room. And they get there because they want to make it easier to navigate. basically. And so they decide that we need to take observations of meteorology at sea so we understand what the currents are, what the weather is on average, so we can plan and do this better. And so this report, you can find it on the internet. It lays out procedures for systematically collecting observations at sea. Interestingly, they are not very happy with the marine barometer. They call it an instrument so rude and so abundant in error, which I thought was great. I mean, the whole thing is pretty awesome, but it ends very, very nicely. They also ask for exceptions for data collection in the times of war, and like it should be treated as a humanitarian thing, right? It's very inspiring, and it ends with this little statement. It is confidently hoped that there will always be full and free interchange of materials. Materials here are data. For it is evident that much of the success of the plan will depend upon this interchange, right? And so this is, like, they are arguing for open data exchange in 1853. I'm going to skip 100 years. Like, all of those ideas get, we do it over telegraph, we do it over mail, we do it with the IMO. In 1947, the WMO gets set up, and its data sharing is foundational, right? So this is 1947, and they talk about how a core function of the WMO is going to be the processing and dissemination of meteorological, hydrological, and related data, right? This actually did blow my mind. So in 1962, this is 6 months before the Cuban Missile Crisis, the US and the USSR agree that we will exchange weather information over a direct communications link between the two capitals. And this is a literal quote from a statement by Lyndon Johnson, right? And so they say, we're going to set up this little system. We will share our satellite data on a reciprocal basis, and we hope that the other nations of the WMO will eventually participate. Like, 6 months before the Cuban Missile Crisis, right? This is amazing. This sets the stage for the World Weather Watch, which I'm sure most people here know, is the WMO setup, where there's a global observing system, there's the global telecommunication system, the GTS, which is a private network that connects, it looks like a whole bunch of capitals, but really the meteorological centers at those capitals, so everyone can exchange data and forecasts. And there's going to be a global network of data processing systems. And all of this is before the internet, right? So this is all private networks being built out between nations. All of this was awesome. It is like the golden period of data sharing until these two show up in the late 80s and 90s. And suddenly there's this big privatization push. Budgets are strained, people are stressed. And this is the kind of setup for Resolution 40, which I had never heard of, right? And it's like, what is this? And it's the background for this. I'm going to actually quote from this report in a lot of detail because I thought it was pretty eye-opening, right? So Resolution 40, the report starts off with, the WMO has adopted thousands of resolutions since 1950, but there's only one that needs no other identifier and continues to be known throughout simply as Resolution 40. This is very dramatic for data sharing. But then he goes, right? So here's a direct quote from Neil Gordon, who is the New Zealand's representative to the WMO. And he's saying, what was happening was that observations collected from a country, example here, France, goes into the United States to be used and ingested into the weather models. Those data would then flow to companies like AccuWeather, no surprise, who would then try to sell this back to France, and the French were not happy, right? And they were getting really, really mad, and they were saying that we would no longer send their data to the States. And again, code is, we almost got to the point where data exchange was being shut off, right? And this is 120 years into meteorological data sharing. Like, there's this long history. And so to me, this kind of left off the page. It's like, this is very, very serious stuff. This is stuff that's been happening for a long time, and it's like under attack. And you keep reading, and like, it's pretty clear that tensions are running high. They're facing the complete breakdown of international data exchange, and there's international media speculation on the likelihood of, to quote, an imminent global meteorological data war. This is a literal quote, right? Like, this very, very strong language is being used, and I had never heard of this phrase. I started searching for it. It is everywhere, and it immediately made me think of somebody needs to make this a movie. You need like a dystopian movie about meteorological data sharing. I would watch that movie. It would be a good summer intern project. Yeah. And for the oceanographers in the room, METAR and buffer are data formats in meteorology. Anyway. So this is the stage for resolution 40. There's a big data war going on. We don't know if data will still be shared, right? And so a group of people get together offline and they propose an argument. The atmosphere in the room is electric. The president invites comment and waits tens of seconds for anyone wishing to contradict. Everyone's looking around. And no national flags are raised. And so like this guy, he's bringing down the gavel. He's saying, we're going to do this when New Zealand asks for the floor. But by then, everyone's already so relieved and happy. They're clapping for a minute. Like everyone thinks this thing has passed, right? But there's a twist. New Zealand has asked for the floor. And so everyone's kind of silent. And it turns out this guy stands up and hands bottles of New Zealand wine to everyone that participated in the debate. Oh, man. And so this report is incredible. And so somewhere in there, he says, like, it passed to thunderous applause. And it was one of those times when grown men and women almost became like children. They were so relieved. This is dramatic stuff for data sharing, right? And so what is resolution 40? It says that it basically defines two different classes of meteorological data. There's going to be essential data that will be shared on a free and unrestricted basis. There's additional data where countries are justified in placing conditions on their re-export for commercial purposes. And finally, for the research and education communities, you get unrestricted access for everything, right? And so this is a hard-won agreement on how to do data sharing under commercial pressures, right? And so the reason I kind of quoted so liberally from all of this and kind of did this history, even though I'm sure there's a whole bunch of you who already know this, was that I found a lot of inspiration here. Like as a community, we've weathered this private sector data storm once. We did it it took a lot of effort and we wrote like a very, very hard agreement. I'm sure not everyone agrees with the compromise that was made. But that generation stood up and it feels like we need to do that again. I also saw it as a measure of how important all of this stuff is. We figured out how to do this before the internet. It survived the Cold War. We've survived one commercial assault before, and it's time to do it again. And then kind of the two pieces that you should keep in mind as we go through the rest of the talk is there's two design takeaways for me. One is a lot of this is top-down infrastructure, right? It's international agreements, national meteorological services talking to each other, sharing data on an operational basis, right, over a private network. And the key persona at the middle of this is the National Meteorological Service, right? And this is kind of foundational. That's important because now we'll switch to oceanography. And the oceanographers are doing something completely different. Who's surprised, right? So the oceanographers are thinking bottom up, and they're focusing on the research oceanographer. And so now we are in 1993, and I'm going to quote from the report on the Distributed Oceanographic Data System, or DODS. And so these, I should point out, like the people that are writing this report are practicing scientists. Like when I did my thesis, I learned a lot of Cornelian and Flow papers. Flow was on my committee. Like these are practicing scientists writing a report on data sharing. And so that's the kind of perspective that DODS comes up with. And so 1993, they're complaining about the rapid increase in the number of data sets available on the internet. So the internet is here, and there's no coordination between these data systems. Any system that's being designed at that time is targeted at large federal archives. But as they point out, a point that is usually overlooked is that most research oceanographers are potential data providers as well as data users. And because of this mismatch that they see between the design of data systems and usage patterns, they're going to hold a workshop to propose something different. And so this is 1993. Over the next 10 to 15 years, we end up building CF, NetCDF, and OpenDAP. So the CF here refers to the CF conventions, so the Climate and Forecast Conventions. This is a semantic layer that describes the data, and it's independent of the actual data format. It's a choice on how, to me at least, it's a choice on how you describe relationships between different variables, and you record the grid and the this and that, all of the important metadata in some kind of standardized form. It's independent of the format as long as it supports arbitrary attributes. NetCDF is a self-describing data format that has the ability to store these arbitrary attributes so we can represent those relationships on disk. And finally, there's a network protocol, which ends up being OpenDAP, a discipline neutral, importantly, data access layer that sits beneath this kind of CF semantic layer, right? And so they thought of it as like these three little pieces. We're going to describe the data, we're going to put the data on disk, and then we're going to let it flow over the network. And fundamental constraints they chose were, we're going to isolate the file format from the data user. We're going to allow data users to access the data directly from their application, and allow users to acquire only those data of interest. So we're going to allow people to subset, so you don't have to download the whole archive to get moving, right? I find this very interesting because I'm not sure the way that I worked as a scientist really met any of these constraints. I was always downloading files. I was never isolated from the file format, and I was always converting things between formats depending on what I needed to do. The same article, 2009, talks about threads. This is Unidata Threads data server, which pushes the idea that a lot of times we're distributing a pile of files when really this is a collection of data as a single virtual data set, right? So that's how you think of the data logically. But it's not how they exist physically. They exist physically as a pile of files. And so Threads puts this idea that we should be doing that as a single virtual data set. It brings the ability to serve those virtual data sets across many protocols, not just OpenDAP, but a couple of other standards that, again, lets you get query data, and WMS, which is, I think of it as Slippy Maps. This is Google Maps view of your data, right? And it does try to isolate you from the format. You can do any of this with any of the formats that it reads, which is a whole bunch, NetCDF, GRIB, et cetera. There's even more in this article. This is from 2009. There's server-side computation services, so stuff like GRADS, Live Access Server. The IRI at Columbia has their own little data library and data analysis platform. And it's all very impressive stuff. But as an oceanographer who started grad school in 2010, I didn't use any of it. Right? I never had access to it. I've never served data over OpenDAP. I never used any of these, right? And that's what really struck out to me. They had this huge vision, and they really executed on it. But somehow that capability stayed in data centers, right? Even though that was not the framework that they approached it with, right? They came from the research oceanographer. And so to me, it seems like we haven't really reaped all the benefits that we could have from all of this architecture that was set up, right? So despite OpenDAP and threads and all of that, we still work with files. And so something that really struck out to me is, why does NCAR collaborate through the file system? We share file paths all the time, and we point people at buckets of NetCDF files. And then everyone stitches them up into their own data cubes separately. We don't have to do that. You could do something else. And despite the focus on the research oceanographer, sophisticated services are for privileged data sets, right? That's kind of how it's kind of shaken out. And my favorite example of this is this NASA State of the Ocean tool, which is, to me, a really, really good example of what is possible. SOTO is run by PODAC, so Physical Oceanography Data Center out of JPL. And it basically gives you the ability to put a whole bunch of NASA data sets on a Slippy map. And so you can pick a time, you pick a data set. To me, it is one of the most effective data discovery tools I've used, because I go to a region of the ocean and then I see what's there. Every time I learn something new, I can overlay chlorophyll over SST over velocities. It's amazing. You go back and forth in time. It's so, so, so powerful. But it's only available for those data sets that are available over there, right? I can't do this with the simulation I just ran. And importantly, this data presentation in the form of these dashboards is very, very inaccessible, I think, to practicing scientists. Like, can you make a Slippy map of your simulation that you ran yesterday? Kind of hard, yeah? I didn't have an answer to that question 3 years ago. And so, 2 takeaways. We haven't really democratized the possibilities that we built, right? There's a lot of stuff that was put out there, but I don't think we fully hit the vision. And I'm going to propose that the way we hit that vision is through a cloud platform. And to argue for that, I'm going to take a little detour into this idea of frictionless reproducibility. So this is a little, cute phrase that's kind of come up in the last year. It was in an article published by a statistician, David Donahoe. I think he's at Stanford. And he spent a lot of time thinking about statistics and computational science and what we would today call data science. He's been doing this for 20 years. And so he's written this article. It's called Data Science at the Singularity. And it's long, but it's interesting. And his core thesis is that something fundamental to computational-based research has really changed in the last 10 years, right? And he's looking at the machine learning community specifically. It's like the rate of progress in this community is incredible, and why is that? And what was interesting to me was he was trying to say was that this is not something innate to machine learning itself. He says it is innate to the culture that machine learning has adopted, right? And so he puts forward 3 principles. Data, which is everything is a data set, and there's a really strong culture of research data sharing. Re-execution, which is not just sharing the code, but the ability to exactly re-execute the same complete workflow. And third is public challenges or benchmark problems, right? And so this paradigm is you put a shared data set, you put up a challenge and a leaderboard, and you have everyone compete to do better, and this sparks innovation. These 3 things, you take it together, they don't seem very new, right? Like, and if you squint, we've been doing this in ocean atmosphere science too. We've been sharing data for a very long time. We're not so great at re-executing completely, but we've been sharing code, doing code sharing for a while. If you worked within the NCAR system, you have the ability to re-execute to some level. The same model simulation. You have access to inputs, the same hardware infrastructure, the same code base. So in theory, you can do this. And maybe the MIPS could be viewed as a version of challenges, correct? And like things like ILAM, CVDP, all of this. Like you're always making dashboards and leaderboards and trying to understand who's doing better and why. So that's not the bit that stood out to me, right? So next, I think he's really onto something with his next bit. He said, in the past decade, all of these ideas have come together as open services. And that's what's different about the last decade. Even the machine learning community has been practicing the other ideas for a while. But what's changed is that all of this is accessible to anyone. And I am not a machine learning practitioner, so I can't comment on the specifics of the argument that he makes. But it really appeals to me, this idea of having frictionless services that offer, as he puts it, immediate, permissionless, complete access to every relevant digital artifact. And then he goes on to argue that empirical machine learning is the field that today most clearly adopts these principles in the form of platforms and services. And he puts up a bunch of examples. These include commercial platforms like Hugging Face, Weights and Biases. These are ways to share data and models. GitHub, and a bunch of more academic, researchy type, nonprofit type platforms. A lot of which were new to me. And so that's the core of his argument, to me, was that we have the computational research community has worked towards these principles of sharing, re-execution, and challenges. But what's really different about today is all of that can come together is a nice platform and service that makes it really, really, really easy to do. And so that's what I think is different about the 2020s, is that we know that platforms are powerful. And I think they're powerful because they define a shared pattern of interaction. And I will try and define this. And I think we all know this from personal experience. We lived through COVID, and we saw all of us immediately switch to a very remote style of working, right? And like, how did we do that? That was game-changing for open science. And we did that over platforms. We did that over Zoom, Google Docs, Overleaf. Someone made a platform on LaTeX, which is amazing. We did it on GitHub, and even the little Jupyter hubs that kept springing up everywhere, right? This was very powerful stuff. And like, I think they were successful because once you learned how to use a Jupyter hub, you could use all of them. Once you learned how to use GitHub, takes a while, but then you get to contribute to basically any package that's on there, right? You now know how it works. At some level, that plays out at NCAR too, in my experience. Right? You do data discovery over emails. You ask someone where this data set is. They point you to a path. You do data exploration. You have a path, so you go do CD, ls, ncdump-8, right? You get to figure out what is going on. And then you analyze any way you want. You can log on to the Jupyter Hub. You can do NCO, NCL, whatever it is. But the point is that this is a pattern that repeats. So if anyone points me to a folder on Glade, I know what I will do immediately to understand what's in there and to start working with the data, right? I think that's very powerful. I think that's, at some level, that's NCAR's secret sauce, right? Is that you have all of this infrastructure that lets you define a shared pattern of working with. And the other cool thing about platforms is they have basically zero marginal cost. The cost of adding another user to take advantage of all of NCAR's stuff is near zero. And the same is true for every cloud platform. The marginal cost of adding a user to Google Docs is nothing, right? They've built it for such a huge scale that it doesn't matter anymore. And that means like things become very, very accessible, and it's very easy to just keep adding people. Some of these frictionless reproducibility principles are clearly being adopted in the earth sciences, particularly in the machine learning pieces. Here are a few examples. The first one on the left is ClimateNet. This is a expert label open data set. I can't tell you much more about it, except that the way this data set is distributed is through URLs that point to netcdf files on HTTP. This is the bucket, right, given to download. The example in the middle, this is from Hugging Face, which is a machine learning focused data platform. This is Samudra, which is a machine learning ocean emulator. And so in this case, they put the model weights on this website that is known for hosting those things, right? And so they've clearly adopted this principle, and they've done it using the platform that is known to the ML community. The last example to me is pretty illustrative of the problem. This is apparently one of the only easily available archives of the German forecasts. It's in ZAR format, and it's on Hugging Face. This was collated by a nonprofit called Open Climate Fix, and put up on this machine learning website, right? And so looking at the first and the last examples, my first question is, where is the DApp? Why am I downloading files again? We've kind of regressed a bit here, right? Like all of this infrastructure was built, and yet, these two very recent examples don't adopt it. Why is that? And so despite all these decades of open data practice, we are yet to fully adapt to the 2020s. And I think it's very important that we do. For one, there's increasing private sector participation in the field that we work in. And they all face the same problems. This is something that's jumped out to me, working with all of these companies, is they're all trying to read buckets or folders full of netcdf files and struggling, right? They're all trying to make sense of it in the same way that a grad student would try to make sense of these data sets. There's clearly an increasing need for public-facing research applications, example dashboards. I remember, part of the whole proposal writing process, close to the end of my time at NCAR, being pretty clear that nearly every proposal was trying to grab at some kind of dashboard concept, some way to communicate results to the public that wasn't an netcdf file, right? And yet, there's all of this cool stuff. Like I talked about State of the Ocean, there's windy.com, which is my favorite example. This is how oceanographers plan field trips, in my experience. They go to windy.com and they grab 3 different forecasts for the duration of the cruise. It's easy, it's fast, it's efficient, it's great, right? This is the future we want. Another big example is this Carbon Plan CMIP6 downscaling exploration tool, which is also it's pretty great, except all of these tools are only available for privileged data sets. It's there for CMIP6, it's there for public forecasts, and it's there for NASA physical oceanography, right? So how do we fully take full advantage of the open source, open science, frictionless reproducibility, all of this stuff? And I think the answer is that we have to change our way of thinking. I think I've tried to illustrate that the persona behind ocean atmosphere data systems kind of starts off with this kind of national meteorological service and countries sharing data. It switches to like a bottom-up oceanographer, a researcher type persona. And I think it's time to like switch that a little more. I don't have a good, cool name for it, except for that it has to encompass the academic, the nonprofit, and the for-profit sectors. And it has to recognize that users frequently switch between 3 different roles. They're either consuming data, so pulling data from, say, a federal archive, they're refining it, maybe coming up with a new estimate, or like combining 2 data sets in different ways. And then they're trying to serve that data out to their community so that other people can use it, other people can build on it, right? And so I think it's inarguable that even as a researcher, all of you are taking on all of these 3 roles at different points in time. And so we need to treat that as kind of first principles requirement. And it's also very clear to me that in the private sector, there are data scientists, you would call them, who also run around between all of these 3 roles, right? They're not so different. And so how do we do that? I think we can put together 2 different concepts. The first one was this idea of cloud-native data repositories. So here's a paper by Ryan and a whole bunch of colleagues, where they put forward this idea that like, the cloud is one way to do this. To fully take advantage of that, you need to have analysis-ready data, which is data that's ready to be used. I think of one example of this is to present it as a virtual cube, not just a bucket of files. It has to be available in a cloud-optimized format, so it works well, and it should be easy to take advantage of all the cloud computing resources that are sitting right next to the data. And so there's this cloud-native data piece, and then I think from David Donahoe's kind of argument, I take away that platforms are incredibly important for actually making any of this stuff useful, right? And what I take away from his article is that the machine learning community is revolutionary because it's figured out how to do that. Like, that's the superpower, right? That they've figured out how to do science on the cloud with all of those three principles. And so if you put those two together, I think you come to what we're building at Earthmover, which is a platform in kind of three pieces that I will show you quickly. There's Array Lake, which is a data catalog, IceChunk, which is a new cloud-optimized and cloud-native format for storing data, and finally Flux, which is a way to deliver data out, right? And so this is, I think, we try to hit all three personas: the data consumer, the producer, and the refiner. Here's an architecture diagram. I'm just going to quickly talk through it, and I'll go into a little more detail. But at the bottom sits the cloud, right? That's the idea. We sit on the commercial cloud because that's a shared space between the nonprofit, the for-profit, and the academic communities. On top of the cloud, you can build a data storage layer. I'll talk a little more about IceChunk, which is a format we've developed in the last few months that is really designed to take advantage of the cloud layer that sits below it. And most recently, just 2 days ago, we released a Flux, which is a data delivery layer that takes the data that's sitting in IceChunk and spits it out on standard protocols, which means you can use your data in any of these tools, right? So yeah, sorry. Okay. Now I'll talk about IceChunk for a little bit. Whoops, I'm sorry. Yeah. So the first attempt at trying to build a cloud-native data repository built around ZAR, which I think many of you have heard of. So ZAR is a format for storing chunked, compressed, multi-dimensional arrays. Chunk just means that a big cube is cut up into tiny cubes. ZAR is open source and open spec. Importantly, it supports arbitrary user-specified metadata. This is important because thinking back to the Dodge report, that's what you need so you can represent the CF and etcdf data model, right? So it meets that principle of being able to represent a semantic layer that is, can vary between disciplines. It is also optimized for cloud object stores, but it does have some shortcomings, which we've since learned since then. It doesn't have this idea of isolation or transactions. So if you are a reader who's reading from a ZAR store that is currently being written to, that is very undefined behavior, and you can end up with bad states. So this can be dangerous. There's no data versioning. This is something we've at least learned is very powerful. In the same way that version control is important for code. And we've since learned that it leaves performance on the table. And so to fix all of that, we've released IceChunk, which is, again, a spec for storing chunked, compressed, multi-dimensional arrays. It is open source and open spec, which is very important. The core library is written in relatively newer language called Rust, which gives us great performance, and it's cloud native. I'm going to justify that bit, which means it scales like the object store. It improves upon ZAR by bringing this idea of transactions from the database community. So this is what allows the concurrent readers and writers to be safe. This is an important problem in production workloads. It brings the idea of version control, so you get things like commits, branches, and tags so that you can version your data sets, which is a pretty natural workflow. And the thing that I was personally most excited about, and I thought would really apply to my workflow as a researcher, is I was always iterating on a data set. And so the idea of version control was very, very important. And I came up with my own ad hoc system. This is better. And finally, the most exciting thing is it formally understands that we like to virtualize files, which is we like to build virtual data cubes that point to existing stores of netcdf files, right? And so it fundamentally recognizes that as a part of the data model and is built to handle that internally. I'm not going to show you a notebook with code, but I'll just throw some code up there because one of the things I want you to do is to go back and just try it out and let us know how it works for you. Here's a simple example. I'm going to open an X-array data set. This is a tutorial data set, but you can open your own favorite model file. It's going to work. You import IceChunk. You tell it where to store data. So in this case, I'm going to do it on the file system. You could replace file system storage with S3 storage if you had access to a bucket and prefix and all of that. And then you create a repository. So this is what initializes a store. And then before you write data, you explicitly tell IceChunk, hey, I am going to write to this store. And so you create what's called a writable session, and you're going to tell it, I'm going to write to the main branch. You can create others. The main is default. And so once you have a writable session, you can write to it in the same way you write to ZAR. So IceChunk sits below ZAR. This is very important, right? So you interface to it through open source libraries. IceChunk is also open source. This is an open source format. And that's it. Once you're done with your writes, they are not visible to anyone who's trying to read from that store until you commit. This is how we get safety. You're isolated from the world until you commit your changes in. And so when you do that, you get a little snapshot. And then you can do things that you may know from Git, like create a tag, create a branch, move back and forth. All kinds of things are possible now. But this is something I think you should all try, because researcher workloads are iterative. You're constantly doing newer and newer versions, and this is software that will help you do that with your data. So what does IceChunk enable? A whole bunch of things. Here's an example, the time series problem. We worked for a little bit with NASA. They have 300 petabytes of netcdf files sitting on the cloud, and it's very, very slow to access. And they have this classic problem that we all have. We've tried to solve it with time series files, where you have stacks of maps, right, as a virtual data cube, and you want to access a little time series, and this involves you hitting every file, and it's slow. But IceChunk is built to do better at that. There's this whole blog post that you can read, and you should. It's pretty interesting. But basically, we worked to build a virtual data cube of references to these netcdf files that NASA already has on the cloud. And we pulled out a time series, a month-long time series, compared it to their current system, which is called Giovanni. It runs on-prem. Details that I don't know, but that workload took 45 seconds. You just do this naively on the cloud, you will end up with 300 seconds. You use IceChunk on the cloud, you get it down to 3 seconds. Right? IceChunk is just that good at fetching bytes that are distributed in many places. And so as my colleague Seba, who likes to point out, it's like once you get that fast, like things just become possible, right? Once you speed up things by 10 to 20x, new workloads are now possible. And so here's an experiment I think you should run. Do you need time series files anymore? Right? IceChunk is cloud native. It scales like the object store. So here's another cool blog post by Seba, where he shows that we got S3 to sustain 250,000 reads per second. This is a completely ridiculous number that is crazy, but if you are a data center who's trying to serve, say, Era 5 to the world, maybe it's not so crazy, right? You have to handle huge loads, and you're going to have to handle a lot of the world coming to you for data. So this is because IceChunk scales like the underlying object store, right? And so I think this is maybe less useful to the academic researcher, but very, very, very useful to the data provider. And so that's data on disk. It's only useful once it starts to move. And so we're trying to build an API layer for serving data out, because remember, most researchers and authors are potential data providers as well as users, which means we care about making our data easy to use and interpret. A core example to this is the idea of building dashboards to communicate to the value of your research or telling stories about your research, right? And how do we do this today? We make our data fit the tool, which is so frustrating. So here's your data set. Usually it looks like a bunch of netcdf or ZAR. And how do you do that? I think it's very common to export to things like CSV, Parquet, GeoTIFF. If you're talking to a GIS person, maybe you export netcdf or map tiles. And that's how you talk to all of this other ecosystem of tools out there that helps you do the other thing you want to do, which is build a dashboard or build a website or build a story, right? And so what if you didn't have to do that? What if your data was now available through a URL across, at this moment, 3 different protocols? So anyone on Earthmover, if you create an IceChunk repo and a branch, you get this little URL that you can turn on, which will enable access over 3 different protocols. The first one is EDR, which is a standard. This is really important. These are all standard protocols. We didn't make our own thing, right? We just make the ZAR data, the IceChunk data, fit the protocol. And so EDR is a way to get time series data out as CSV. So you give it a point, you get back a time series. This is a thing that we've seen many private companies rebuild again and again on their own. There's WMS, which is how you build state of the ocean for your data set. This is why I'm excited. WMS is Slippy Tiles. It's like Google Maps, right? And finally, DAP, because it's classic. And once you serve data over DAP, you're compatible with the whole netcdf ecosystem. And so you can nc dump -h a URL on Earthmover. So putting it all together, here's a super quick demo of a data set that I worked on and published a paper on in 2021. This is an MIT GCM ocean simulation that was run by Scott Bachman. I'm going to show it to you in 3 ways. The first is in our data catalog, Relic. And so if you log in, you'll see a lot of information about your data set, how much you use, how much data are flowing in and out. I spent a lot of time yesterday building these demos, and so you can see I read like 30 gigabytes. I'm going to click in. I'm going to click into a specific repository. I'm going to also zoom in. And so I ingested a very, very small fraction of the data. Just for demonstration purposes, look, I've given credit to NCAR because that's where I ran the simulations. There was only 5 variables. A bunch of these are coordinate variables, so time, longitude, latitude, depth. Theta is temperature, or seawater potential temperature. So immediately you can see that we're giving you a viewpoint into the data set. This is NC-dump-8, but on the web, which I'm very excited by. These arrays are 4 dimensions, so there's time, lat, long, and depth. And if I click up to history, this is where I will show off. I made this data set in 2 commits. The first was creating the repository with IceChunk, and the second was actually writing the data. I can click into this to see a cool diff that tells me that I added 6 different arrays, and it turns out that that theta array had 1,076 chunks, right? So it's visualizing the changes that you've made as you've ingested the data. So that's a Relic. The thing that I'm most excited about is this. So this may or may not work. This is going to be that data set, but shown on a Slippy map. Look at it. It's beautiful. Those are tropical instability waves. And if I go on the left, here's a time slider, and this should work. This website sometimes has trouble with our data, but let me try this again. Come on. There it is. It's coming. So clearly, this talk is about possibility. It's not about polish, but look at that. I was so excited when this showed up. This was my data in my personal state of the ocean. I could do this on my own. And it was like click a button in the UI to enable the service, right? We still need to figure out how to make this work well. This particular GIS platform has trouble. But the point is the possibility. You can do this. This is a regional ocean model simulation on an external platform that has no idea about oceanography. Final demo, here's a Google Sheet that I'm going to stick in a lat and long to do a query. Maybe you need this because you're trying to build a nice website. The way this works is, again, there's a nice little, I'm going to zoom in. There's a nice little URL you can ping. This is serving data over the EDR protocol, which is going to come back as a CSV format. I send in a point with lat and long and a specific time. And there it is. So I'm going to zoom out so you can see the full figure. This is a vertical profile of turbulent heat flux in the ocean at, I forget what point. It's kind of near the equator. You can see there is a lot of mixing above 100 meters, which is above the equatorial undercurrent. You'll also see that the simulation has 2 grid point noise, which is not great. But this is in Google Sheets, and it's like turbulent heat flux, which is very, I get a kick out of it. I don't know if you do, but this is just game-changing for telling stories about the research you do, right? That's what it says to me. So putting it together, right? There's a lot of technology here. There's lots of details here, but I think the takeaway you should have is that the cloud lets you build things for everyone, right? I had no idea about GIS, really. I barely understand this WMS protocol, but I understand that it lets me put data on a map and lets me drag around and drag sliders, right? And I think this is really, we're getting really close to realizing this vision that was put forward in the first DARDS report of the research oceanographer should be a core component for anything you build, right? And so all of these services should not be available just for privileged data sets. It should be for everyone. As a really cool example of all of that, here's a research group that we've worked with over the last year. This is at the University of Wisconsin on a project called A-Life. And so what they're doing is estimating GPP, gross primary productivity, from satellite data, right? From GOES-R specifically. So this is geostationary. It's coming back at very high frequency. And this is a research group with grad students who are orchestrating a pipeline in the cloud to deliver near real-time estimates. I think this is just amazing. So the data lands up in Google Cloud, I guess, straight from the satellite, gets run through a little inference service that they run on the Google platform. They make an inference, they write it to Czar, and they stick it in a Relay, at which point, they're serving to the world, right? These guys, they've run workshops against us. It's just pretty amazing. And this stuff was just published. I think it's finished review. And my mind is still blown that all of this stuff is orchestrated by graduate students, right? And I think we're getting closer to just making everyone, use this technology and make it easy. So to conclude, I've had this idea stuck in my head for a while, but preparing for this talk has made it very clear that everything old is now cloud native, right? As a community, we've worked on open data practice for more than a century, which is just impressive, at least. And it's clear that the fundamental ideas are not new, right? We have to share data because weather and climate are global. The way we express those ideas has changed, and it needs to adapt to available technology. We've done one of these transitions before, right? We've switched to use the internet in ways that, and it has worked well for data distribution. Like, we can actually share data with each other. It's just hard. We are yet to realize the full promise of the cloud. And I think this is important because I find Donahoe's argument very compelling that cloud platforms can be very revolutionary for science. And he's kind of arguing that this is what is special about the machine learning field today. And so what I think we need to do as a community is figure out how to democratize all of the stuff that we've built so far. And I think at Earthmover, we're trying to do exactly that in our own little special way by trying to build up a storage layer, a data delivery layer, and a catalog layer that's kind of cloud native, works really, really well. With the whole idea that we need to make our data and our stories more accessible. So if you're interested, we'd be very, very happy to chat with you. My email's up there. Thank you for listening. Thanks.
So much. Great talk, Deepak. Any questions here in the audience? And we also have online. Please add your questions to Slido if you have any. Go ahead.
This was really cool, especially the demos at the end. But where does the data that you were looking at on the web actually live?
It lives in S3.
So
On AWS?
AWS S3.
Amazon Web
Yes.
Services.
So I actually downloaded 4 NetCDF files from RDA, because that's where I archived it when I published. And I dumped it on the cloud. I wrote it to a Relay, but that just writes to S3. And then I turn on the service, and that's it. So it's 3 steps.
So awesome stuff. So I got to ask about, I guess, chunking when it comes to, would you consider, it sounds like for anyone serving the data, you have some chunking choices to make to serve up the data, right? And do you, because so many different researchers, take Airify, for example, I imagine would have a wide potential variety of chunking schemes that would optimize for their own particular workflows. Do you suspect that would be a bottleneck for some researchers in this platform, and what are potential solutions? I guess as one that I potentially thought of, is it feasible at all to have a different versioning system, different versions of the same data hosted with different chunking schemes, or is that cost prohibitive?
No, exactly. And so you're totally right that this one implementation detail of how the data set is cut up is incredibly important for depending on what workflow you're doing. We're brainstorming ideas for how to get around this, but our vision is that is an implementation detail that should not be exposed. And, storing the data multiple ways is one. I actually see ice chunk, because it's so fast, has just changed the envelope on that quite a bit, right? So we may still need multiple copies, but maybe not as many as we would have in the past, right? But this is something that we're trying to experiment with, and then most importantly, we want it so that it's easy. You should not have to think about this problem. We can solve that problem for you. And how do we build software and a platform that does it for you? I think that's what we're coming to.
Do you have a question, Dan?
Yes, thank you. Nice talk. You mentioned data set versioning. I was wondering if you or others, is there some way of just saving the delta when you update a data set? Because one thing we're running into is when you get this proliferation, you have to host all these huge data sets.
That happens at some level in ice chunk. You have to be careful about how you make your update. But if you've only changed the last time step, that's the only piece that duplicates, not anything before that, for example.
What about sometimes we have these QC changes that might affect multiple times, but still a subset of the data. Is there some way of compressing that?
Yeah, so not as implemented today. There was an earlier version of this where we cared a lot about deduplicating. So if we had a chunk with exactly the same data, it would always be stored in just one place. But that ends up having lots of downstream consequences that we didn't like. It makes it harder, for example, to delete a version that you don't care about because it's referenced in many places. So not specifically that way, but there's, depending on how those updates work out, there are ways where IceChunk would help you today.
Do you have a question? Then we'll look at online.
Yes, thanks for the talk, Deepak, that was great. From was it Hugh Donahoe? One of the phrases that you had was about reproducibility. I forget the adjective that was before it.
Frictionless.
Frictionless reproducibility. And reproducibility on one hand sounds like a wonderful aspiration. On the other hand, it means very different things to very different people. Yeah. And I can think of lots of different interpretations that to achieve reproducibility are either practically impossible or are frictionless. How do you interpret that word? And what are with this workflow and this stack, what sort of reproducibility are you trying to accomplish?
I agree with you. And I buy into the idea that reproducibility is important. But again, the details matter so much, right? And so the thing that I really took away from that paper was he wrote it as reproducibility. But I think what he really means is sharing workflows or sharing ideas. Like fundamentally, that's what he means. Right? He means the idea that you can hit the same input data set, you can run the same workflow. Maybe it doesn't do bit for bit, right? Which is something we don't care about. But it's so close that it really unlocks something new. And in his telling of the whole story, it fits into this idea of having competitive challenges. And so someone can solve the problem, and then you can pull their solution and tweak it. This kind of iterative. And so I agree that maybe there's details he's not addressed about things like bit for bit reproducibility and stuff like that, but I think he's arguing that it's gotten a lot closer, and these platforms that help you do that and make it easy are a key part of it. That's how you switch the cultures, because it's just so easy to do. I buy into the idea of reproducibility, but I have never really worked too hard to make it happen, right? Personally.
Take a couple of the online questions. Tell us more about virtual chunks.
I think this is the aggregated virtual data set idea, right? So in IceChunk, every chunk can be, you could optionally just be a symlink out to a different file. So when you ask for a particular subset of data, depending on what's recorded, you could be getting it from an netcdf file, or you could be getting it from a native binary blob. So that's just the idea. It's tracked deep down inside IceChunk so much so that the difference does not matter in any meaningful way. You don't have to do anything special once you create the store.
This was great. I'd love to work with you to demo how analysis workflows running on e.g. Casper, which is our data analysis and visualization machine, could process data through these APIs and check their performance. Logical result is making it easier to develop workflows that can run on and off-prem unmodified. Okay, I don't know if that's a comment or if you have any comments.
Yeah, I mean, we'd be happy to try it out. It's definitely going to be work to be done. But
That's my question, Sky. You talked about, okay, for my workflow, I had to download these files and put them in S3. How do we get rid of that? How do we connect this
the two
institution to the commercial cloud better? Because I don't foresee us going to the commercial cloud completely in the near term, but maybe at some point. But you're going to still have these NSF or DOE research facilities. How do you integrate them better with this ecosystem?
I'm with you on we should make those connect better. There's no reason I had to download that. I should have been able to hit that open app or something, right, and just run it all remotely.
Right. Okay.
No, I agree. I'm with you on that.
How much does this performance depend on being on Object Store S3?
Truthfully, I don't know how to answer that question because we've mostly just worked on Object Store, and so this is something someone should try with Luster. It'd be interesting.
We've done some experiments on, GPFS and HTTPS, and we don't see a big difference. It depends how performant the system is locally.
Yeah,
But most people don't have access to a big giant file system. That makes kind of a big difference, yeah.
I don't think like the performance is the key unlock here in IceChunk. It is super important. It enables a whole bunch of new things, but for like the average researcher, I think version control. That's the thing that appeals to me personally.
Do data sets get DOIs? I don't know that your service is.
No,
Yep.
not at the moment, but an idea we've thrown around.
Can you discuss data egress charges as a significant friction in using object store services for sharing public data sets?
Yeah, this is a very good point. My personal view on this is that this is just a challenge that we will need to figure out. And I think that because I just think that the public cloud is such a big enabler of new things that it is important that we solve that problem, right? And so, in some level, as a community, we figured out how to solve the payment problem today. Like, NSF pays for NCAR, and then a whole distributed community uses NCAR resources. They come to NCAR, right? So I think hopefully there's like a similar model that we can find that works for it. I'll say for the university group we work with, Alive, their costs are all part of the grant. There is an Earthmover line in their budget, right? And so that's how they paid for it, and that's how they're paid for it now. If that's a different model, then you democratize the costs. So I don't know about data egress specifically, but I could see there being like an NCAR corner of the Amazon cloud or something. Maybe that's the way that it goes, and then there's also little research groups everywhere that pay for it out of their budgets, if it works for them.
Megan, you have a question?
I wanted to ask about latency and the region of like hosting the data. So essentially you want the data to be closest to where your users are, and technically you can host it like anywhere, even like Amazon is true. So like, do you keep a duplicate of the data set in each of the for each main region, or?
At the moment, we don't do anything. It's up, like, it's all in one. But yeah, that's one of those things that I keep hearing about.
All right, any final questions at all? I guess I have one more. How do you get people to start using data cubes instead of buckets of files and hardwired scripts?
By providing them
Internally.
stores.
Okay.
Yes.
Does it work with different types of software languages? Is that a dependency?
Yeah, at the moment it's very Python heavy, but this is something we're hoping will get fixed very soon. The core library is Rust, which has really good interrupt story. And so, but we need to do the work to tie it up. But if you're in Python, it all works really well today. And I think, yes, we should be providing data cubes to people. We had this idea 20 years ago.
Okay, thanks everybody, and thanks again.